Hello everybody, welcome back. So today I'm going to be talking about a couple more basic derivative rules, the derivatives of sine of x and cosine of x. But before we do that, I'd like to talk about the Squeeze Theorem as well as a couple of special limits that'll be important in the derivations of these two derivatives. So the Squeeze Theorem is another tool that we can use to evaluate limits. And what the Squeeze Theorem says is that if we have a function f of x, call this f of x, and we have a second function g of x, and then we draw a third function that's always, or that over an interval containing a specific x value, say x equals c, right here. You see our third function, let's call this h of x, is always in between f of x and g of x at every single point on an interval containing x equals c, say, let's say from here to here, or from here to here, or from here to here. Except maybe at x equals c itself, when one or more of them may not be defined. Like they may have little holes in their graph. So if f of x and g of x both have the same limit as x approaches c, and h of x is between them at every point within an interval containing x equals c, then this function h of x must have the same limit as f of x and g of x do at that one point. Think of it like when you're grabbing onto, or you're about to grab onto a piece of chalk. At first, your fingers are very widely separated from the piece of chalk. But the piece of chalk, you get it so that it's between your fingers, and then you start moving your fingers closer together until you're pinching the piece of chalk. And then your fingers in the piece of chalk are all converging on the same point. So you can think of the Squeeze theorem like that. And sometimes it is called the pinch theorem or the sandwich theorem. But that's the general premise behind the Squeeze theorem. So from the Squeeze theorem, there's a couple of special limits that we can find. These limits are the limit as x approaches 0 of sine of x over x equals 1, and the limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. Now, I'll show a proof of this first one here. It's probably not a proof that you'll really ever need to know. It's just kind of cool to see how, like, the interesting ways that we can get proofs of these limits. And it's a proof that's kind of out of left field in a sense. Like, you'd never expect this to be a way that we prove this limit, but it is. And I'll start by drawing a unit circle. So a unit circle is a circle centered on the origin with a radius of r equals 1. So we know on the unit circle we have, let's say we have an angle theta right here. So we know that this point here is cosine of theta, sine of theta, because any y value on the unit circle is the sine of the value of the angle theta that makes with the horizontal, and the x value is the cosine of the angle theta made with the horizontal. And then, if we continue outwards and draw this line here, we get that this one here, this point up here, is the point 1 tan theta. So what we can do is we can split this into this one sector in this triangle here and this triangle here. We know the area of the sector is equal to theta over 2. The area of this, and I'll label this one triangle 1, and I'll label this one triangle 2. You know that the area of triangle 1, which is this triangle right here, is equal to 1/2 times its base. Its base is just 1, because this radius is 1, times its height. Its height is the y value of this point here, minus this y value. This is 0. So the height here is sine of theta. So we know area 1 is equal to sine theta over 2. And we know that the area of our second triangle is equal to 1/2 times its base, which is also 1, times its height, which is its y value here, which is tangent of theta. So we know that this area 2 is equal to tan theta over 2. So now we want to create an inequality. We want to squeeze something. So in this case, what we have is that we know that the area of this triangle 2, this big triangle, is going to be the biggest out of all of the areas. So we have A2, which is tan theta over 2, is greater than or equal to, in the middle area, is going to be the area of this sector. So this is theta over 2 is greater than or equal to the area of this small triangle. And the area of this small triangle, A1, is sine of theta over 2. So now I'm going to erase this drawing because I need to, actually, I'll continue the problem over here. So, none of these, though, are sine of theta or sine of x over x. We're looking for something in the form of sine of x over x. So we could multiply through all of these functions by something. The question is, what do we want to multiply by? So we've got, say we tried to make this one here sine theta over theta, because this one looks like it's the closest. The problem with doing that is that this sine of theta over theta would be one of the endpoints. It would be our function g of x, the function at the very bottom, which would be like your thumb when you're going to grab the piece of chalk. It's the bottom function. What you're looking for is the function that would represent where the piece of chalk is, the one right in the middle. So our function right in the middle, in this case, is this one, theta over 2. So we need to find a way to get this to be sine theta over theta. So let's start by multiplying this by 2 to get rid of this 2. And then we have theta, but we want a sine theta. And so we want sine theta in the numerator and theta in the denominator. So if theta is in the numerator, we would want sine theta to be in the denominator, and then we could take the reciprocal. So I'm going to multiply this through by 2 over sine of theta. And what we end up with is tan theta over sine theta. And remember, tan theta is equal to sine of theta over cosine of theta. So tan theta, which is sine theta over cosine theta, divided by sine of theta, with these twos canceling out. This just cancels to give us 1 over cosine of theta. So we have 1 over cosine of theta is greater than or equal to theta over sine of theta, which is greater than or equal to, in 2 over sine theta times sine theta over 2 is just 1. So now, if we can take the reciprocal, but when we take the reciprocal, we have to flip the greater than or equal to signs. The reason is, say you have 3, and 3 is less than 5, right? So if you take the reciprocal, you have 1/3 versus 1/5. But we know 1/5 is smaller than 1/3. So when we take the reciprocal of a bigger number, it becomes a smaller number. So we take the reciprocal of each of these and we get cosine of theta is less than or equal to sine of theta over theta, which is less than or equal to 1. But notice that this proof is, or this here is for theta is greater than 0. What would happen if theta was less than 0? Because remember, we want this to be true over an interval containing theta equals 0. So we want it to work for positive theta as well as a negative theta for a certain range. So let's try plugging in negative theta. We get cosine of negative theta is just equal to cosine of theta. 1 at negative theta is just 1. And sine of negative theta over theta, we know that sine of negative theta is equal to negative sine of theta over negative theta. The negatives would cancel out and we still get sine theta over theta. So this works for, let's say we were to draw this here as well. It will still work. So it does work within a certain range from a negative theta to a positive theta, which is exactly what we want it to do. So now we can take the limit of each of these as theta approaches 0. So limit as theta approaches 0 of cosine of theta is equal to, when we try direct substitution here, we get cosine of 0, which is equal to 1. So we see that 1 is less than or equal to the limit is theta approaches 0, sine of theta over theta, which is less than or equal to, and the limit is theta approaches 0 of 1, is just 1. So we see that this function, cosine theta, and the function 1 over an interval squeeze sine of theta over theta, and they both approach 1 as x approaches 0, meaning that sine of theta over theta also has to approach 1. And there's the proof of this one. And it's really actually kind of neat that it's something that you'd think was completely unrelated to, aside from maybe the sign, was unrelated to circles, certainly unrelated to area. Like, you'd never think that this is the way you go about proving it. But it's really cool to see that that is how you go about proving that. So now that I've talked about these two special limits, I'd like to talk about the derivatives of sine of x and cosine of x. And I'll leave the, we also have the limit x approaches 0 of 1 minus cosine of x over x equals 0. It looks like I erased that one unintentionally. So let's say we wanted to take the derivative of sine of x. We know that this is equal to the limit is x, or is delta x approaches 0 of sine of x plus delta x minus sine of x all over delta x. And this here comes from the limit definition of the derivative. So the first step is going to be simplifying this. And we have a little formula for when we have something like this. We know sine of a plus b is equal to sine of a times cosine of b plus cosine of a times sine of b. So we can expand this term out. When we do that, we get limit is delta x approaches 0 of sine of x cosine delta x plus cosine of x sine of delta x minus sine of x all over delta x. So what I'm going to do is I'm going to take this sine of x and group it with this sine of x. So we get that this is equal to the limit is delta x approaches 0 of sine of x cosine of delta x minus sine of x plus cosine of x sine of delta x over delta x. So now what I'm going to do is I'm going to factor a negative sign out to the front. So this gives us that this is equal to the limit as delta x approaches 0 of negative sine of x. So when we factor out a negative sine of x, this term would become negative cosine of delta x. And this term would become positive 1. So we get negative cosine of delta x plus 1 over delta x plus, now I can take this part of the fraction of the limit and split it off into its own. And we get plus cosine of x sine of delta x over delta x. Now I can split this one limit into two limits. I can say that this is equal to the limit as delta x approaches 0 of negative sine of x times 1 minus cosine of delta x over delta x plus the limit as delta x approaches 0 of sine of delta x over delta x times cosine x. So we look at this here, 1 minus cosine delta x over delta x. And this here is this special limit here. this will evaluate to be 0. So we get this term here cancels out. So for this term, this here, sine of delta x over delta x, is this special limit here, which gives us 1. So this will become 1. And in terms of this problem, you see we're taking the limit as delta x approaches 0. We can treat this cosine of x as a constant in this problem. Like if we were to plug delta x in directly, we would end up with sine of 0 over 0 cosine of x, because the x isn't the variable that we're working with. We're working with delta x here. And same here with this negative sine of x. So this tells us that the derivative of sine of x is equal to the cosine of x. And then we can prove in a similar manner that, and let me write these up here. So we have derivative sine of x is equal to x. And in a similar manner, we could prove that the derivative of cosine of x is equal to, the derivative of sine of x is cosine of x. That's my bad. And then the derivative of cosine of x is equal to negative sine of x. This one, number 2, can be proven in a similar manner. I'll let you give that one a shot. Try that one out for yourselves. So, now that we know these, let's do a couple of examples. So example 1, let's say f of x is equal to 3 sine x. Now for the examples, go ahead, try these out on your own, pause the video, and then once you think you have the answer, continue watching. So, let's start. You want f prime of x is equal to the derivative of 3 times the sine of x. From the constant multiple rule, we can bring this 3 right out to the front, and this gives us 3 times the derivative of sine of x. We said the derivative of sine of x is cosine of x, so this gives us 3 cosine of x. So now, example 2, let's find the derivative of x squared plus 2 cosine of x. So the first step is to use the sum and difference rules to split this derivative into the derivative of x squared plus, and then we can use the constant multiple rule here to say 2 times the derivative of cosine of x. We know the derivative of x squared from the power rule, multiply the power by the coefficient, we get 2x, and then subtract 1 from the exponent to the 2 minus 1, plus 2, and we know the derivative of cosine of x is equal to negative sine of x. Make sure you remember that negative there. That is important. So we end up with this is equal to 2x minus 2 sine of x. So example 3. the derivative of sine of x plus cosine of x plus 3e to the x. So we can use the sum and difference rules to split this into 3 different derivatives. We can say that this is equal to the derivative of sine of x plus the derivative of cosine of x plus, and once again invoking the constant multiple rule, 3 times the derivative of e to the x. You know, the derivative of sine of x is sine of x. You know, the derivative of cosine of x is, or the derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine x. So this is cosine of x minus sine of x plus 3 times the derivative of e to the x is e to the x. Sorry about that. Sine x, cosine x get confusing sometimes. Happens to all of us at one point or another, trust me. So then, let's do one more example. What's the derivative of pi cosine of x plus 3e to the pi plus pi squared sine of x. So we can split this derivative using the sum and difference rules into 3 separate derivatives. Now pi is a constant. So for this first one, the derivative of pi cosine of x, we can use the constant multiple rule to bring the pi out to the front. That becomes pi times the derivative of cosine of x plus the derivative with respect to x of 3e to the pi plus pi squared, once again pi a constant, derivative of sine of x. Now the reason that I didn't bother to take the 3 out to the front of this middle derivative here is that 3e to the pi is a constant. And we remember the derivative of a constant is 0. So this middle term actually is 0. So this first term is pi times the derivative of cosine of x is negative sine of x and plus pi squared times the derivative of sine of x is cosine of x. So this gives us pi squared cosine of x minus pi sine of x. So that'll do it for today's video. Hope it was helpful, and thank you all for watching. Next time, I'm going to start talking about the product rule, and then after that, it'll be quotient rule, chain rule, and then some applications of differentiation. So once again, thank you all for watching. Hope you enjoyed. Hope this video helped. And I will see you in the next one.